Hey students, it's Mr. Arnold. We're going to run through some stuff on Earth systems and plate tectonics. And it might seem like this is a little out of our wheelhouse for environmental science, but it's really not. The question that sort of pops up when we say we're going to talk about the Earth systems and tectonic plates and earthquakes and all that is, why would we worry about that? I mean, what does that have to do with environmental science? Well, I mean, essentially it has to do with this, that all the resources that we have and all the elements, all the compounds, all the chemicals, all the things that we talked about as far as cycles, and all the nutrients and stuff that we need for both for all the biosphere and for human consumption, they're all set when the Earth was formed. And so the way that the Earth shifts these things around matters a lot to us. So when we talked about these cycles like the phosphorus cycle, we mentioned that a large part of it is what's going on in the rock cycle, and that's going to be true in the soil formation for the nitrogen cycle, and how the rocks move, and how that the lithosphere interacts with the biosphere for the carbon cycle as well. So let's run through real quick just basically what the structure of the Earth is then. So you've got the inner core here in the middle, okay? That's solid, again, metal, iron and nickel for the most part. You've got a molten outer core, and then what is going to start to matter a little bit more to us is we get to the mantle here in this yellow part. Now this is basically what we think of as like this yellow part in the middle, the mantle. This is basically what we think of it as magma. This is obviously hot and molten. The upper layer of the mantle is known as the asthenosphere, okay? And this is sort of semi-solid, semi-liquid. It's really ductile. I mean, we could say that it's molten in a sense. I mean, it's liquid in the sense of being a fluid. It can flow a little bit and move around, and that's going to be pretty important to us. And then we've got a solid upper mantle here. That is for the most part solid. Again, it's right above the asthenosphere. I mean, like where the boundary is a little hazy. And then on top of that, we have the crust. Okay, and the crust, of course, is the solid part. Now, when we say solid, we don't just mean the continents. This includes the oceans as well. They're floating on the crust part. So this is the solid part of the upper Earth. And if we take the crust and the solid part of the upper mantle together, this is what we talked about when we talked about the lithosphere at the beginning of the year. So we said that we had these four spheres that we were worried about. We're worried about the atmosphere, which we talked about in the last unit, and the hydrosphere, which is water, we're going to get into in the next unit. The biosphere obviously sort of encompasses us for most of the year. So the lithosphere is the rock part that we're going to worry about. So the bulk of what we want to talk about here all revolves around the idea of plate tectonics. Back in the early 20th century, a guy named Alfred Wegener, who was actually a meteorologist, he came up with this theory at the time that was called continental drift. And so he believed basically that the Earth's crust was moving, okay? And he came up with this idea that at one point all the continents were connected into a supercontinent that he called Pangaea. And if you look at this animation over here to the right, it's sort of showing this, and right now it's at the point where it's sort of breaking apart, but you'll see it'll come back together. This is what he meant by Pangaea, where it's all one big continent. And so his theory was that these continents drifted apart eventually, that they were one big continent in Pangaea and that they split apart. His reasoning for that is that he said there were similar rock formations. If you looked at this part of South America and this part of South Africa, you would see very similar rock formations. And what they found as time went on, and initially no one really believed this theory, but as time went on, what they found was that there were a lot of fossil remains that were found in both places. And there was obviously no way that these land reptiles were going to make it from Africa to South America without leaving some fossils in between somehow. So their rationale was then that there must have been some way that these things were together. As the 20th century went on and they were able to study things a little bit more underground, they found that this was indeed the case, that the Earth is basically the lithosphere, okay, the crust, is essentially divided up into different plates, or divided up into these subregions that we're going to call plates. And these are in constant motion. We call this motion the tectonic cycle. So, I mean, here's basically what the plates are. This isn't all of them, but this is the major plates at least. We're going to divide these up into two categories, oceanic and continental plates. Continental plates tend to be a lot lighter. That's why the continents are there, because their vast bulk of them is silicon dioxide, and so it's a lot lighter, and it's going to float on top. The oceanic plates tend to be a lot heavier, a lot more iron and heavy metals and stuff like that, and so they're going to sink down and be a little heavier, and so the oceanic plates are going to be a little bit below where the continental plates are a lot. And that these are the things that are moving apart from each other or moving towards each other, depending on which direction that they're going. And this has all kinds of implications for us, particularly with the rock cycle that we'll talk about in the next unit. And that's where it's really important for us. The rock cycle plays a role in generating soil, but all kinds of implications for life and for human life on the whole, because the movement of these plates is essentially where our activity, our volcanic activity, and earthquakes and stuff like that are all going to come from. Now, it's important to remember that those plates that we just talked about, they're basically floating on top of the mantle. And what's kind of interesting here is, so when we talk about weather, we talk about convection cells. If you remember, we talked about Hadley cells and polar cells and mid-latitude cells, Ferrel cells, all that stuff. Convection cells, there are convection cells in not just in the air, they're in the water as well. We'll get to more of that later, but we saw a little bit of that with the ocean currents and the thermohaline circulation. But there's actually convection cells going on in the mantle as well. Remember, the mantle is basically liquid magma, and so as it gets heated up, it's close to the core and it gets hotter the closer it is to the core down here, and then hot liquid rises, okay, just like hot air would rise. And so as it rises up, it's going to rise up, and it's essentially going to start to sort of replenish part of the crust. It's going to push up new material here, and as it rises up, of course, and gets to the top and starts to cool off some, it's going to start to cycle back around, okay, and come back around just like we would have a Hadley cell working in the atmosphere, okay. So this is pretty important. These convection cells are basically why we think the plates move. This is the plate tectonics part of it. These convection cells drive this. The place right here, and I missed this arrow a little bit here, sorry. Right here where the one plate is sliding under another, this is what's called subduction. Okay, so you got plates coming together. Oceanic plates are heavier than continental plates, and so the oceanic plate goes down under the continental plate. That's going to have all kinds of implications. You can see here that we're getting a trench formed there. It's also going to form some mountains. We'll see here in a second. And so if we look at all the different things that are going on plate tectonics wise, and there's a ton of numbers here. Don't worry about this. This just happened to be the diagram that I pulled down off of Wikimedia. But there's a lot of definitional type stuff that we need to know here. So these at the top here, these are basically the three different ways that plates can meet. Okay, when plates are against each other, these are the three different sort of plate boundaries that we have. So right here we've got transform plate boundaries, and that's where you've got two plates and they're next to each other and they're sliding past each other. Okay, they're not separating, they're not coming together. One of them's not going under the other one. They're sliding against each other, and as you can imagine, if you got two massive plates of the crust rubbing against each other, there's a lot of force there and a lot of difficulty or a lot of problem that can come about for that. We'll talk some more about that in just a second. The one that's labeled number 9 here, this is what we call a divergent plate boundary. So you got two plates and they're spreading apart from each other. Okay, that goes back to those convection cells down at the bottom. So if you look down here, this is a good example of a divergent plate right here. Remember the magma, hot magma is coming up. Okay, and it's going to cycle around, and as that happens, it's cycling in both sides, and so you got two plates that are basically forming new material. Okay, where the rift there is, new material is being forced up out of the mantle and added to the crust, and then it's going to cycle back around. Okay, where it cycles back around is at a convergent boundary here at number 8, and that's again where the oceanic plate is going to slide under a continental plate. And as that happens, you can see here, as the crust starts to sink back down into the mantle, it's eventually going to basically melt as it gets back down into the magma. And then it's going to cycle back around, and the process keeps going. Now, this is pretty important to us because where this magma comes up in these places, this is pretty important because we're going to get new material, okay, that we basically didn't have access to before. We don't really have much access to the mantle. And so new material, new minerals, iron, copper, silver, all these things, they're going to come up in these areas where the divergent plate boundaries are. Now, it's not just at plate boundaries that these things happen. There are occasionally some hot spots in the mantle where the fluid gets really heated and it basically just sort of shoots up through the crust. Those hot spots are pretty important. The whole island chain of Hawaii is essentially formed from this, and we get a lot of volcanic activity where these hot spots are. They tend to form a lot around plate boundaries, but they don't have to. Hawaii is out in the middle of the Pacific plate, and it's still a hot spot where the stuff is coming up. So hot spots are pretty important there. So hot spots, divergent, subduction, convergent boundaries, and then we've got a transform boundary right here. Maybe the most famous transform fault that we think about is what's called the San Andreas fault. A fault line basically is that you've got an area where the two plates there are together, and it's basically deformed the rock and sort of made it really kind of brittle. And what's really cool is this is actually an aerial view of the San Andreas Fault. You can actually see the fault line where the rocks come together there. And if you look at this map of California, this is the San Andreas Fault here. You'll see there's another fault down here, the San Jacinto Fault down at the bottom. But again, transverse boundary here where the North American plate on this side and the Pacific plate on this side are basically just rubbing up against each other. As you can imagine, that can cause some problems. And occasionally what happens is that there's basically a slip. Normally, it moves at a rate of about 1.4 inches a year. That's how far plates move when they're diverging or converging, or even as they're slipping past each other on a transform fault. But once in a while, a lot of energy will get built up and it'll all get released at once, and they'll really slide past each other really rapidly, a few meters in a matter of seconds, which doesn't sound like much, but if we're talking about a whole plate sliding meters, that's a really violent activity, and that's basically where earthquakes are going to come from. And so if that happens down here, usually it's going to happen way underground, that slippage is going to occur. And then obviously that's going to affect everything on the top of it. So this little diagram over here, what we always hear about on the news is the epicenter. The epicenter, basically, we think that's where the center where the earthquake occurred. Actually, the epicenter is the part right above where the earthquake occurred. It's the part on the surface above where it occurred. The hypocenter is actually where it occurs down here at number 2. Number 3 here, that's the fault line, as the plate there would be subducted underneath it. So if we look at the boundaries here, this basically is a map, and again, the plates aren't labeled here, but if you look at the boundaries here, you can sort of tell where all the plates are. So we got divergent plates, like down the middle of the Atlantic is a divergent plate. It's called the Mid-Atlantic Ridge. And so the magma's pushing up, and it's got this ridge, sort of this under ocean mountain complex, all the way like just a line down the middle of the Atlantic. And the Atlantic is basically splitting apart. And so what that means is that the North American plate here and the Eurasian and the African plates here, they're moving away from each other. Okay, they're diverging. And so what was proposed at one time is that Pangea, they were close together. That divergent plate is going to force them further and further and further apart. And so that's actually the case. North America and Africa and Europe are actually getting a little bit further away from each other every year. We see little bumps here. Those are convergence zones, and so that's where an oceanic plate is basically diving under a continental plate. And a really famous example is over here in the Western Pacific near China, and this is where we get the Marianas Trench. This is the deepest part of the Earth. I want to say, gosh, I can't really remember, but I want to say several miles down is the Marianas Trench there. The transform boundaries, you can see those are the solid black lines, and you'll notice that there's one right there in California. A few other places where the plates are slipping, but those are kind of big ones there. And then we've got hot spots here, and you see that Hawaii is one, and there's a bunch out in the middle. Hot spots can be where volcanic activity is. That's generally what's going on. Volcanic activity is not confined to hotspots. In fact, about 85% of volcanic activity is right along plate boundaries. In fact, this area right around the Pacific here is called the Ring of Fire because there's so much volcanic activity around that particular area as all those plates, as the oceanic plates, the Pacific plate dives under the other plates. Now, why does this matter to us environmentally? Well, I mean, first off, there's a lot of human impacts. I mean, human lives are impacted and lost every time there's an earthquake. You think about the Haiti earthquake back in 2010, about 200,000 people were killed. So that's a pretty big deal. And obviously volcanic eruptions, I mean, you know, all the way back to Pompeii and further back than that. I mean, there's human impacts from that. Weather patterns can definitely get disrupted and air quality can be affected. You think of a volcanic eruption, there's a lot of ash that's spewed up in the air. A couple of years ago, there was a big eruption in Iceland, which again is one of our hot spots. And that disrupted pretty dramatically air travel. They couldn't fly planes in that area because they were afraid the planes were going to go down as all that particulate matter hit them. And obviously the air quality is going to be pretty badly affected. It can affect the weather patterns in other ways because they're not going to get as much sunlight if there's a lot of volcanic ash up there. Basically blocking the sun. When we have these big volcanic eruptions, the average temperature of the globe actually goes down a little bit. And of course there's a, you know, for us and maybe in smaller areas, but there's a pretty big deal with habitat destruction. If there's a big volcanic eruption like there was in Mount St. Helens back in 1980, that essentially just destroyed that entire ecosystem. There was nothing left. It was almost like a nuclear explosion had happened there, and really the same sort of energy had applied. So, I mean, these things do matter to us a lot environmentally. In the next video, we're going to talk about the rock cycle, where it's going to impact for us a lot more because that rock cycle is eventually going to lead into soil formation. But plate tectonics is still important for us, enough to know what's going on and to be able to put those sort of underlying things with the other impacts that we're worried about.